This is the Earth Science Classroom. Welcome. This is Topographic Maps, Contour Lines Part 2 video. In this video, we're going to look at, to continue on from Part 1, which looked at the definition of a contour line, how to draw one, contour interval, and basic rules. This video is going to continue with the rules and discuss more about gradient and slope and how we calculate gradient, looking at the contour line shape, the V or W on the contour map, what it means, and also look at fluvial systems. Now, as a very quick recap from video 1, a contour line is a line that connects equal elevation or height on the Earth's surface above sea level, can be in meters or feet. They do not cross or intersect and must have only one elevation per one location on the Earth's surface. Every fifth line, as you can see on this map on the left, every fifth line will be darker, and that is an index line that has an elevation on it generally. And also that the distance between the contour lines indicates gradient or slope, or what the Earth's surface looks like in terms of the elevations. Are going uphill or downhill, and we can interpret that from these lines. And the closer they are together, the more steep the gradient and the landscape, and the further away, like over here, is going to be, or definitely over here on this part of the map, top left, is going to be more gentle gradient, more gentle slope. All right, so to move on and to add more onto the gradient and slope, we know that we can figure out the contour interval, or the CI, right, based on the index contour lines. So let's say this is 100, okay, and then this is 200. So there's 5. There's 1, 2, 3, 4, and 5, and there's 100 difference by 5 equals 20. So our CI equals 20. Now, why does this matter? Well, because the elevation difference between the contour lines does not change, because the contour interval is pretty consistent over the whole map. That allows us to see, now if I'm looking at a side view, okay, here is 100, right? And then this one here will be 120, because you add 20, okay, because the interval, add 20, so this is 120. So I'm going to go uphill from 100 up to 120. So we know it's going uphill in that direction, right? Okay, so now if the lines were closer together, this 100 would move here, because what happens is this map, these contour maps, you are looking from an aerial perspective, from where the bird's eye view, so looking down onto the map, seeing here's one contour line, and then here will be the other contour line, but the further away they are, the gentler the slope. But if they're close together, right, and you've got to rejoin those lines together, so it's 100 and 120, this line is a lot steeper. So the closer the contour lines are to each other on the map, for example, on the map right here, or right here, the area would be steep, because you have to keep the same difference in elevation, which is 20 feet, which is our contour interval. So you express the gradient through how wide, or the distance between each contour line. And the closer it is, the steeper. The further away, far away, the gentle. So close is steep. Okay? So in terms of representing gradient or slope, now gradient is the steepness of the surface. Slope is the angle of which goes through a certain point, more of a math term. So this is more of a math term. But we use gradient in geoscience. Now, gradient is, or calculated by, rise over run, or the change of field over the distance. So this basically is a change of height, which is the field. Change of height or elevation. And run would be the distance. So how far you went and how high you went up, right? So this triangle obviously is created, and slope is up here. So if I'm going to be up here, okay, trying to walk up this slope from point A to point B, okay, I want to calculate the gradient of that slope, of that hill, whatever, going uphill. So obviously you'd have, you know, walking distance, but you kind of walk up here. You walk up the slope up here, which is not really the distance. So if you actually use a little bit of Pythagorean theorem, okay, and A, B, and C, what you'll have is, okay, you want to figure out C, or actually you want to figure out A. You have C, because let's say you walk up the hill, right? You walk up the hill. And let's say C is 50. And you know that the change in elevation is 20. So B will be 20. Okay? So you want to figure out what A is. Okay? So A squared equals 50 squared plus 20 squared. All right? So that's what? Let's see. Oh, not X, or A, sorry. A. So A squared equals 2,500 plus 400. So basically, if you add that up and then square root that, you will get an answer around 45.8. So this actual number right here, which you don't actually have because you're walking uphill, you can't walk through the ground, would be 45.8, okay, based on the other values we have in the experiment. So you can have that and you can calculate that with a little bit of Pythagorean theorem and work in with a little bit of math. So again, just to confirm and show the distance, how close they are and how far they are, looking at these two diagrams here with contour lines on this topographic map, you have the same kind of contour line elevations from 20 to 80, 20 to 80 on both sides. But you'll see that these are really close together and these are far apart, or compared to each one. Now there's this dashed line here that you can see right through the middle of both diagrams. Now if I transfer that to a cross-sectional profile of both those diagrams, and I'm going to draw a cross-section along this dashed black line to show you the steepness. I've added in the elevation on the y-axis, and the x is both distance. So in terms of the steepness, okay, I'm going to actually go like this. So we got 20 here, we got 40 here, we got 60 here. I'm going down like this and showing where they are. So 80 is up here, 60 is right here. I'm just plotting my x and y graph. There we go. So if I draw it, I've got this kind of gradient. Okay, like that. So it's kind of gentle. Whereas if I do this map here, I've got a lot shorter distance with the same change in elevation. So I assume it's going to be more steep. So my 20 is here, come down, the 40s there, come down the 60s here, and 80s there. So there is my gradient. As you can see, over a much shorter distance, I've increased the same elevation change from 20 to 80, and this is a much steeper gradient. So you can tell both from the contour lines on the map how far apart they are. You can relate that and transfer that to a cross-section profile where it's showing you the actual steepness. And you can, again, if you had the distance, you can use the rise over run to calculate the exact gradient of both slopes. Now, next rule is in terms of rivers or fluvial systems. So rivers, streams, brooks, tributaries, all based on, obviously, gravity and the direction of flow. All right, stream flow. Now, this can be linked and modified into any kind of fluvial discussion, topic, anything like that. So if you have a landscape at top of a map, and you have contour lines, and you have the same contour interval, which is 20, right there, my 2 index lines in red. Now, if I'm going to draw a river down here, okay, I want to know basically now, we know that the highest elevation on this contour map you can see is 200. So, and here is 100. So this is the direction of going downhill and decreasing elevation. So we know that water flows downhill due to gravity. So, but if you're not sure and can't see the elevations posted on the contour lines, then you can use another thing to figure it out. The actual contour line will make a U or a V, depending on the valley that it's flowing through, okay, or the ridge it's coming from. So if it has a V shape, then it's usually a valley cut by water. If it's a U shape, it's cut by a glacier. So it depends on latitude, location, and history of the area. So you can tell. But let's just say this is a U. As you can see, there's a U here. There's a U right here. I'll do it in purple so you can see. A U, and a U, and another U. There we are. And there we go. So you see all these U shapes going over the river. Now, this U shape is pointing this way. Now, the bad thing is that it's opposite. The water, the flow, is opposite the direction of the U. So right now, again, it confirms with the elevation, is the stream flow is flowing in this direction. It is opposite to the U. Okay, and as we know, it goes downhill through because of the elevation change. So on a contour map, you're going to have lines, and if you don't have any kind of obvious elevation marks, that it's going to be difficult to figure out if it's uphill versus downhill, or any kind of features that the land may present. For example, a ridge or a valley. Now, a ridge is a higher elevation, and it's going to be either a hill or a mountain, depends on elevation, and it's high relief. So the shape of the land. Now, generally, a ridge will be a set of concentric circles. Now, concentric means that they all go around a central point, like a archery target, like this. And the distance between each line would vary, but it all goes around a central point. So this central point right here would be the summit or the peak of that particular ridge. Now, it could be circular, it could be different shapes, could be different elevations on the peak, but it's going to be concentric circles. Now, on the sides would be various gradients, and obviously that would be dictated by the climate and the weather and erosion, and also the geology, the structural geology as well of the ridge. But a valley is the kind of opposite. it's the opposite to a ridge. So it's an elongated depression. So a depression is an area where the surface actually decreases in elevation. Like a crater or a pothole or a cave system, but there's some sort of like basin or decrease in elevation on the Earth's surface caused by some sort of process. So an elongated depression. It could also be a gully, which is primarily formed through the flowing of water downhill. As its obvious opposite, it's going to be low relief and show lower elevation than the surrounding area, like the Grand Canyon, for example. All right, so next rule I want to look at is in terms of depressions or a decrease in elevation in a certain area on the map. And these are indicated by hasher marks, basically. And they look like this. So this set of concentric circles, all right, if I add in some, well, it doesn't matter, even without any kind of like contour elevation numbers on the lines or any kind of index lines, you know that this is going to be lower. This is going to be lower elevation than this area right here. But if I add in, let's say, 300 and also add in 300 here, that means that this is a flat area right here, and that the lines repeat to show on either side of a ridge or a depression. So you show two the same elevation contour lines to indicate the top of a mountain or where the depression starts, and you see a lower elevation, and you see these like black hasher marks that would indicate a depression on the top of a map. And as shown in a cross-sectional profile diagram, this would be a similar kind of diagram, not exactly the same, but where you'll see this area right here. You'll see this is where the depression is located, and this is how it's shown on a cross-sectional profile, where you have this like dropping down or dipping down of the gradient in a certain area on top of the hill, and you'd see those hash marks right here to indicate this depression, just like we have right here. So this will be a side view of a similar depression at the top of a ridge. So to recap overview in part 2, these contour lines create complete loops and shapes. Even if they go off the page, they still complete the loops and the shapes of equal elevation and height. Gradient is the calculation of rise of a run and used in various profiles to show and illustrate gradient and slope and differences. We use V or W patterns on the contour lines to signify fluvial systems and where they flow, river flows, and also to distinguish ridge and valleys, which are different relief and landscape features on the top of a map, which you can see through elevation. And also we're looking at depressions, which is the lower elevation areas, the areas where the ground sinks down deeper into a lower elevation. And we discussed the repeating contour lines around a ridge or summit to indicate where a depression would be and where the summit of the ridge would also be as well. All right, thanks for listening, guys.